Yes, sir, I did. I was taking a look. Sorry.
But if yours is not updated, and same thing with Minashi, I guess. Yeah, Minashi. I have Shravya's here. Parvati's also is not updated. Excuse me, sorry. So let us discuss these questions and then we can move on. Yeah. Yes, Parvati, can you name, what did you name this first molecule?
Yes. M-methyl phenol.
M means meta, right?
Yes.
Okay. Let me just plug in my. M-methyl phenol. What about the B1?
Meta-bromotoluene.
Yeah, correct. Meta or again M-bromo toluene. Okay. Khalil, you want to say what the C1?
Sir, M trinitrotoluene.
M कैसे होगा? M होगा. Okay, one more thing. This OMP na, it is only used when you have disubstituted. If you go here and when I started naming these things, I said that nomenclature for disubstituted benzenes. That means you will have only two substituents. So, and in the question also I have written write the name of following using base name and the OMP wherever applicable. So in this case it was not applicable. In this case you had to use it was, yeah, I can say it as following. Fine, the base is, yeah, we can have the base but not the OMP, not the OMP. So this will be 1, 2, 3, 4, 5 and 6. So this will be named as 2, 3, 6 trinitro toluene. It is also known as TNT. Okay, it is an explosive. It is an explosive. Okay, what about the D1? Khalil? Okay.
Yes, sir.
What? Yeah, the D1.
Sir, isopropyl benzene.
Yeah, correct. It will be isopropyl. Benzene. What about E1?
Ethyl benzene.
Ethyl benzene. Yeah, very good. Correct. Okay. Now let us move on to the aromaticity part. So you tell me, what about the first one? Guys, aromatic. It is aromatic?
Yes, sir.
Okay. It is aromatic. What else do we have? This is aromatic. N is equal to 6, right? N is equal to 6. Aromatic. I just had to add a negative charge here. I forgot to add a negative charge. But the lone pair itself saying that it is aromatic. Okay, fine. What about the next one? Is it aromatic, non-aromatic?
Not aromatic.
It will be
Not
not
aromatic.
why not aromatic?
N is equal to 5 by 2.
N is equal to how much?
Oh,
This
no, talking about the B.
sorry, B1. Okay, fine. Tell me about the B1.
N is equal to 5 by 2.
N is equal to 5 by 2.
Oh,
So is it because it's not planar?
Wait a second. Khalil, you are asking, can we write that as toluene? M hydroxytoluene. I was talking about that. A1.
Yes,
Yes,
sir.
Khalil. Yeah, you can write it, but again, we use phenol because it has higher. You know that OH is a functional group also, right? In the list of functional group. That is why preferred way of writing is M methyl and phenol rather than M hydroxytoluene. Okay. Okay.
Yes.
No, if you write that, it will be fine. Well, if you write that, it will be fine. But the only reason why I'm teaching this OMP method is that sometimes you will be in books, you'll be always saying M methyl phenol. You will be never saying M hydroxytoluene. That is why I showed that M methyl phenol, because the use of organic nomenclature is not that one question will come for IUPAC nomenclature. That is not the use. The use is that they will give you to write a reaction, and in the reaction they will be writing the reactant. They will not be drawing the pictures. They will be writing the reactants, in the reactant's name, and then they will be asking you to react it with some reagent. Then they will be also asking you to write the name of the product. Okay, so in those cases only IUPAC nomenclatures come hand. As for questions directly from IUPAC nomenclature, there will be one or two. Okay. Next is okay. B1. What did you say? N is equal to how much? 4n plus 2. It is equal to how much?
12.
Yes, 12. Fine. It is equal to 12. Okay. Now, acha, can you see that both of them are benzene? Yes or no?
Yes.
Okay. So can I say that? What about this structure? This is one ring, na? It will be aromatic or not? This ring will be aromatic.
Yes.
Okay. What about this ring? It will
Aromatic.
be aromatic, है ना? So once you see that these are not fused rings, right? They are not fused with them. They are attached rings. They are attached rings. That is why in this you have to see that both of these rings now they are not connected. They are connected by a bond. They are not sharing a particular bond. For example, if I talk about this ring is sharing this bond, right? So this bond inside we can see that there is a bigger ring inside that, है ना? This is a
Yes,
bigger
sir.
ring, but I cannot make any bigger ring if I talk about the B structure. That is why in these cases, you have to see individual rings here. So since this is also aromatic, this is also aromatic, hence the whole molecule will also be aromatic. Okay. What about this structure D?
Aromatic.
D will be also aromatic, right? Because how many? 1, 2, 3, 4, 1, 2, 3, 4, 5. So 10, yeah, 6, 4, 10, and 14, correct. So N is equal to 10 here. That is why this also will be aromatic. Okay. Now let us move on to this is 20. Okay, so let us write the preparation of benzene and its homologues. Preparation of benzene. So one of the preparation you must have seen while we were learning about alkenes. Okay, preparation of benzene. You remember any reaction in which we had benzene as a product? No?
So polymerization.
Yeah, cyclic polymerization of ethyne. Cyclic polymerization. Cyclic polymerization of ethyne. Now, what happens in cyclic polymerization of ethyne? We have ethyne molecules, right? CH, triple bond CH, and in a red hot tube, right? And we get benzene, and we get benzene. So this is a reaction we have already discussed. Next slide, decarboxylation of aromatic acids. Second one, decarboxylation. Of aromatic acids. Now, in this, we have benzoic acid. We will use benzoic acid. And when benzoic acid, it is treated with NaOH, it will give you sodium benzoate. It will give you sodium benzoate. And then on further reactions, there will be more reactions happening and it will be forming benzene. Please write. You have COONA. And you react this with a base NaOH in the presence of calcium oxide. Now, this is a reaction that we have. Similar type of reaction we have seen in the alkane case also. You will get what? The benzene ring plus CO2. So this is known as decarboxylation. Now, when the CO2 will react, then it is going to form Na2CO3 with sodium hydroxide here, going to form Na2CO3. There will be some heat required here. The third reaction is even more easier. The reduction of phenol with zinc dust. The OH. You react this with the zinc metal, but it powdered zinc metal, give some heat, and you will be getting benzene. Some zinc oxide will be there. Write this down. Let me know if you're done. So these are the only three reactions that you need to know for the preparation of benzene. For the preparation of benzene. This is done, guys. The Pvt is done. Okay. So most of you guys are done. Is there anyone who is not done? Please let me know. I will scroll up. Okay, I will scroll up. Right, next. The physical properties. Okay, physical properties of benzene. The physical properties. First thing is that these aromatic hydrocarbons, these are what? These are non-polar molecules. Okay. Aromatic hydrocarbons. Are non-polar. Non-polar molecules. They are usually colorless. They are usually colorless. Next point is that they have some characteristic aroma. Characteristic aroma. So you have seen those naphthalene balls, right? Naphthalene is what? It is fused benzenes, two benzene which are fused. But they cannot technically say that they have some fragrance in it because it is not very good smelling thing, but it is not also very bad smelling. But it has some strong aroma and it has some strong smell. Okay, it has some strong smell. Some people they will like the smell of naphthalene ball. Some people won't like the smell of naphthalene ball. Okay, so that is why it has some characteristic aroma. You can it smells different. You can see it smells different. Next is, since they are non-polar, since they are non-polar, since they are non-polar, they are immiscible in water, but dissolve in but they will dissolve in organic solvents. Organic solvents. Write this down. Let me know if you're done. Okay. Next are the chemical properties. Next is the chemical properties. Okay. So in chemical properties, what do you think? Let us look at the structure of benzene. Let us look at the structure of benzene. So we have benzene with 3 pi bonds. And also remember that it is resonating, right? It has resonance in it. That means the pi bonds are alternate and they can move to places. And hence the resonance hybrid will be the resonance hybrid. If I can draw the resonance hybrid, then you will have benzene ring and it will be something like this. That means inside the ring we have an electron density. We have some electron density. Okay. So first of all, the question that is raised here is that benzene, it is electron rich or electron poor? Can somebody answer me that? What do you think, guys? What can we say about benzene? It is electron rich or electron poor? Yes, tell me. Okay, one question. Alkene, you see with alkene and alkynes, what were they? They were electron rich or they were electron poor? You can flip your pages back to notes. Parvati, tell me.
Electron rich.
Yeah, they were electron rich. Now in alkene we had 1 pi bond. Here we have 3 pi bonds. So obviously benzene is also going to be electron rich. Yes or no?
Yes, sir.
Okay, fine. Now if it is electron rich, then it will be reacting with electron poors. Yes or no?
Yes.
electron rich, it will give electrons to electron poor species. That means it will be showing electrophilic reactions, right? Electrophilic reactions. That means, and the reagent, it should be electrophile. The reagent that we are using, it should be electrophile. That means it should be an electron loving reagent, an electron loving reagent. So electron loving means the best electron loving reagent or substance would be something. It would be something which has a positive charge, which has a positive charge. So generally we don't have anything which has a positive charge, but if there is a chance of creating a positive charge in a particular reagent, then we will use those reagents. Okay. Now, electrophilic substitution reactions are the most common ones. So we will look at a series of electrophilic substitution reactions. So let us just start. Now, first of all, let us look at a general mechanism, how it will attack a particular, electrophile, and how the reaction is going to happen. So general mechanism, if I will start with electrophile, then I will have this benzene. And we are just assuming that we have got a charged species here. Okay, we have got a charged species. We have somehow generated this charged species. How are we going to generate this charged species? It will depend on what reagents are we using. That is another that we will be studying on each of the reactions, how these electrophiles are generated. But we have generated an electrophile. Let us look at how the benzene will be reacting with this electrophile. So obviously, electron rich to electron poor, the movement of arrow will be something like this, from electron rich to electron poor. Now you can say that, let us assume that this bond is broken, this pi bond is broken, and we can have the electrophile in any one of these. Say that electrophile is here. There is one hydrogen in each of these carbon. You must remember that. Okay, please remember that all of these carbon, it has one hydrogen each because it has only having 3 bonds. The 4th bond will be satisfied by the hydrogen. Now, as you can see that in this pi bond which was broken, it was made by 2 carbons, the black carbon here and the red carbon here. Now, this black carbon initially, it also had, both of them had 4 bonds. Now, this black carbon, it has 4 bonds even after the addition of electrophile and breaking of the pi bond. But our red carbon atom, at this point of time, the red carbon atom, it does not have any bond. It just has 3 bonds here. The 3rd bond is with hydrogen. Now, since this carbon has lost an electron due to the breaking of pi bond, it will gain a positive charge. Okay, it will gain a positive charge. The next thing is that as you can see now, there are many chances of resonance here. So this positive charge, it can move around. The positive charge can move around, and you can see that. Let me just erase this. We don't need it right now. Oops. Okay. Positive charge here. And the resonance will be A double bond B, single bond C, and there is a positive charge. So this type of resonance will be shown. You can draw some more structures. Now there's a bond here. The electrophile is here. The hydrogen is here. And this bond is broken. Now this carbon, it already had all the bonds. This will be having a positive charge. There is a double bond here. Now this double bond can move this side. And you can have, and then you will have a double bond here, have a double bond here, and then you will have a positive charge here with the electrophile here and the hydrogen here. Okay, and the hydrogen here. Now, the next case that is going to happen, the next thing that is going to happen is you have this structure. That is the electrophile and the hydrogen and the positive charge here, 2 pi bonds in this case. Now, we will have something that will abstract hydrogen. you will be having something that will abstract hydrogen. It will be most probably something in a negative charge. So let me write just Y negative will be there. What is this Y negative? So again, it will depend on which of the reactions are we looking at. So it will abstract the hydrogen like this. Okay, very dramatic way of showing the abstraction. So it is will be now, since it is abstracting the hydrogen, the 2 electrons, it will be shifted towards this bond here, and then you will get again the aromaticity will be retained. You'll get 3 bonds here, and there will be an electrophile that is attached in this benzene. This is a general mechanism how this is going to happen. Now we have only 2 things. We know how the benzene is going to attack on the electrophile, and how this carbocation that we are making, this carbocation which we are making, it is stabilized. It is stabilized due to resonance. It is stabilized due to the resonance. Now we know this, but our question is 2. What is this electrophile? How should we generate this this positive charge thing? And what is this negatively charged thing? That is going to abstract the hydrogen. So for this, first of all, write the first reaction, that is the electrophilic substitution reaction. Number 1, nitration. Okay. Now, in nitration, let me just write the reaction. You will use obviously a benzene, plus for nitration you will use 2 reagents. One is that is concentrated H2SO4 and concentrated HNO3. Now both of them will react at somewhat high temperature, let us say 333 Kelvin, and they are going to form a nitrobenzene. Plus some water. Now, first of all, we know that this NO2 is our electrophile, but let us see how this particular NO2 is formed, how this NO2 is formed. So generation of NO2 positive, because this is going to be our electrophile. Whatever substituent is added here, that is going to be our electrophile. How it is generated? So we have 2 reagent here, H2SO4 plus HNO3. Now, we all know that H2SO4 is a stronger acid. Then what it is going to do? It is going to abstract OH negative. It is going to abstract OH negative from the HNO3. And it is what it will be having. This will be acting as a base. This will be acting as an acid here. So it will be liberating H plus. This will be liberating NO2 positive, because if I remove O and H, I will be left with NO2. One oxygen has been removed and one hydrogen has been removed because it is acting as a base. Now this will get a positive charge. And you will be having plus HSO4 negative, because this H2SO4 has released a H plus ion, and they will be the H plus and the OH negative will be forming water. Okay. Now this is the water that you see in the product, but now we have got our NO2 negative. Now what it is going to do? It will attack on the. Now it will do what? It will attack on the benzene ring. Okay. So right here, NO2 positive plus benzene. It is going to attack like this, and it is going to form. Okay. NO2, and this bond will be broken. There will be getting a positive charge here. There will be a hydrogen. Now this HSO4 negative is the negative reagent which is going to attack on the hydrogen atom. So you will have, write the bonds. And this bond will be shifted to the benzene ring. And this is how you are going to form nitrobenzene. So this is the generation of NO2 positive. The second step will be attack on benzene. Yeah, wait a second. Abdurrahman, wait a second. And at last, removal of proton. Chemical properties, yeah. Let me know if you're done, Abdurrahman. Done, okay. So you can write this down. Let me know if you're done. If you want me to scroll down, I can scroll down. But you need to remember that it is forming nitrobenzene. A nitro group is added on benzene. If you react, the reagents are nitric acid and concentrated H2SO4, sulfuric acid and nitric acid. Yes, done, guys. Let me know if I can scroll down. Okay, Parvati is done. Okay, right, next. Right, next, halogenation. Okay, next, halogenation. You can write a statement. Arenes means benzene or benzene derivatives. Okay, benzene or benzene derivatives react with halogens in the presence of Lewis acids such as, you can use many things such as anhydrous, AlCl3, FeCl3, FeBr3, okay, to form haloarenes to form haloarenes. So you'll have benzene plus, let us say, Cl2 in the presence of AlCl3, and you are going to get a chlorine group which is added on benzene. A chlorine group which is added on benzene. Now, in this case, let us see how is the generation of electrophile taking place. How is the generation of electrophile taking place? So generation of, now what will be the electrophile? Cl positive. Generation of Cl positive. Okay, so how is this going to take place? So you have chlorine. I will scroll up now. Just listen now. No, don't write like this. Okay, listen now, then I will scroll up. So you have Cl plus Cl, and then there is AlCl3. So aluminium is making how many bonds? Aluminium is making how many bonds?
3 bonds.
3 bonds. So is the octet complete? Is the octet complete?
Yes.
Yes. And how?
No, yeah, 6
No,
electrons.
6 electrons only, right? So that is why this is a Lewis acid. That means it wants to abstract electron. Now, what has electron? Chlorine, it has lone pair electrons, right? Now, it needs electrons. So what it will do? This bond, it will attack on the aluminium, and aluminium will attach itself with one of the chlorines with its electron. Now, aluminium was completely neutral. Now it has attached itself with one of the chlorine atoms, and that is why it will get a negative charge. So this is AlCl4 negative, plus you are getting Cl positive. Okay, plus you are getting Cl positive. Now the same thing will happen. The Cl positive, it will attack. It will attack on what? Attack on benzene. Now the attack of benzene will be something like this. Okay, this will be the attack on benzene, and after that we have to remove the proton, right? We have to remove the proton. So what is going to happen? Removal of proton. We have AlCl4 negative. So AlCl4 negative, it will attack with one of the chlorine atoms. Okay, to hydrogen. Hydrogen will shift the electrons here. That is going to form. The chlorine will attach itself to hydrogen. So you'll get AlCl3 plus chlorine and hydrogen. They will form HCl. They will be forming HCl. Okay, so you can write now halogenation. Done, guys?
Can you scroll down?
Yeah, sure.
So the last one,
Yes.
benzene doesn't have chlorine on it.
Sorry. Thank you for. Yes. Okay, is there anyone who's left? Is everyone done? Yes, Khalil, Abdurrahman, Mazia, Mehreen, Minashi. Okay, seems everyone is done. Right, next, Friedel-Crafts alkylation. Friedel-Crafts alkylation. Okay. Now, in this reaction, as you can write, when benzene is treated with alkyne halide, in the presence of anhydrous AlCl3, presence of anhydrous AlCl3, it forms alkyl benzene. Alkyne benzene. So, for example, let us start with this CH3 Cl, the presence of anhydrous AlCl3, it is going to give me alkyl benzene. Okay, so CH3 will be attached. Here, what is the alkyl? The CH3 is alkyl, and you will get HCl. You can have numerous reactions, right? Plus, let us say you have the Cl is attached here. Again, the same thing, anhydrous AlCl3. You have to just keep in mind that the point of attachment will be that carbon atom which had halogen attached to it. Halogen attached to it. That means this carbon is going to attach on the benzene. So you get, okay, you'll get a molecule like that is isopropyl benzene plus HCl. This is something that you have to remember. The point of attachment. Okay, the point of attachment. Now, in general, I can write. In general, I can write. If there is a benzene ring and a haloalkane, that means Rx, it is treated with anhydrous AlCl3, then the R group is going to attach on benzene. Plus HCl will be formed as a byproduct. Write this down. Then we'll look at the generation of R positive. Okay, generation of R positive. Done, guys? Let me know if you're done. Okay. Generation of R positive. Okay, generation of R positive. So you have Rx plus AlCl3. Let me write RCl only. Okay, let's take that case that this is RCl. Now AlCl3 is going to attack on RCl. R will be R positive, plus this will be AlCl4 whole negative, as it was the case in the halogenation reaction. Then is attack on benzene. So you have R positive plus we have benzene here. Now this is going to attack like this. Wait a second, did I mess up with any of the attacks? No. No. This is going to form R, there will be H here, and the bonds will be here like this. Then removal of proton. So we have, there will be a positive charge here. Let's say, put, yeah, this is positive charge here. We have this, and here we have hydrogen. Here we have the R group plus AlCl4 negative. It is going to attack on the hydrogen. The hydrogen is giving the electrons to the benzene ring, and you are going to form alkyl benzene like this, plus AlCl3 plus HCl.
So can you scroll up?
Scroll up, okay. This much?
Sir, a bit down.
So from generation of,
Yes.
yeah,
yes.
okay. नहीं पे था? Generation of R positive, no?
Yes, sir.
Yes, guys, done. Okay, since you guys are done. So write a note here. This is important, okay? Write a note. This is important. When benzene is treated with, when benzene is treated with 1-chloro propane, it forms isopropyl benzene. It forms isopropyl benzene. Why is that? See, when we have one chloropropene, so let us see what is one chloropropene. We have CH3, CH2, CH2, Cl. Now, while the generation of electrophile AlCl3 will react with this, it will be reacting with AlCl3. And what is going to happen? We are going to get CH3, CH2, and CH2 positive, and CH2 positive. Thus, obviously, you will be getting AlCl4 negative. Now, when we have a 1 degree alkane, when we have a 1 degree carbocation, what happens is that, as you can see, that this is a positive charge, and this hydrogen, it is present here. This hydrogen, what it will do, it will shift its bonds towards this carbon atom. It will shift its bonds towards this carbon atom. It is something like hyperconjugation that is in the organic concepts, the previous chapter, basic concepts of organic chemistry. Now, this is called as hydrogen shift. What is going to happen if it will shift this electron to that carbon? You can write it in this next reaction. We'll have CH3, CH, H, and CH2 positive. Now, this is known as 1,2 hydride shift. 1, 2 H shift. Okay, 1, 2 H shift. Now it is going to form CH3, CH, CH3, and this carbon will be having a positive charge. As you can see, this is 1 degree carbocation, right? And this is 2 degree carbocation. The number of alpha hydrogen in this case, for the hyperconjugation effect, it is just 2. And the number of alpha hydrogen in this case, it is equal to 6. So there is a high increase in the number of alpha hydrogen. That is why due to hyperconjugation, the stability is higher for the 2 degree carbocation. Now this 2 degree carbocation is going to attack on the benzene, right? This 2 degree carbocation. So you have this benzene ring. You have this benzene ring. And I can write this as positive charge, right? It is a 3 carbon atom, 3 carbon molecule, and which has a positive charge. So this will attack on this positive charge. And the benzene is going to get attached with an isopropyl group rather than a N-propyl group. So you can write here like this. It is attached with isopropyl group here. Okay. So write just 2 arrows here. It represents, if you have 2 arrows, it represents that after a few steps, then this is going to form, because we are not writing the removal of proton steps. Okay, because we have already written that in the mechanism. So you can just write 2 arrows, which shows that after a few steps, this will be formed. Right, since secondary carbocation is more stable than primary carbocation, there is a hydride shift and there's a hydride shift and 2 degree carbocation is attacked by benzene to form isopropyl benzene. Write this down. Let me know if you're done. The Parvati, Minashi both are done. Okay. Right next, Friedel-Crafts acylation. This is, I guess, fourth. Friedel-Crafts acylation. Now, in Friedel-Crafts acylation reaction, write a statement with me. Benzene is treated with. When benzene is treated with. Yes, sure.
Benzene.
Done? Okay. When benzene is treated with, we have two things you can treat this with. You can either treat this with acyl halide, or you can treat with acid halide. We will show the structures. When benzene is treated with acyl chloride, or rather you can generalize this to acyl halides. Or acid anhydride. Or acid anhydride in the presence of Lewis acids, it forms acyl benzene. Forms acyl benzene. So what is acyl halide? First of all, let us see. This is our benzene plus acyl halide. It means you will have a carbonyl group with a halogen here. Let us write chlorine here, and here you will be having CH3. Okay, so you will be having CH3COCl in the presence of anhydrous AlCl3. Anhydrous AlCl3 with some heat, you will be forming a benzene ring, and in this benzene ring, there will be a COCH3 group attached. Okay, so this guy here, it is our electrophile. So what is the electrophile? This carbon atom, it is having the positive charge. So you will have CH3, C double bond O, and here you will be having a positive charge. Okay, here you will be having a positive. This carbon is going to attack on the benzene. Okay. Now this is the same thing that is going to happen. AlCl3 will attack on the Cl, AlCl4 will be formed, then you will be having AlCl4 negative, which will be removing the proton. Okay, similar type of steps will be going on. You can also have benzene plus, you will have benzene plus, you can have C double bond O, which is attached to CH3, bonded to oxygen, and this oxygen is again bonded to C double bond O, CH3. This is known as acid anhydride. These are example of anhydride. Okay, now again here, this is your electrophile. This is going to be your electrophile. In the presence of same thing, AlCl3 and some heat, you are going to form acyl benzene, carbon, double bond oxygen, and then CH3. Right? So this is what acetophenol. So write this down. Let me know if you're done.
So what are the other products found?
Now in this reaction, you will be having HCl because that chlorine and hydrogen will be attaching. Now in this case, you can see that, let me draw this with some different color. This is going to be the negative part. Okay, this is going to be the negative part, right? Now, here
Yeah.
this was the negative part. Now this also attached to hydrogen. This will be also attaching to hydrogen, and you can see that it is forming CH3COOH, right? CH3COOH. Write this down. Let me know if you're done.
Sir, can you scroll up for
Yeah, sure. Yeah, done. All of you?
Yes, sir.
Okay. Right, the last one, that is the sulfonation. So what is this going to be? Fifth one, I guess. Sulfonation. You can write here. When benzene is treated with hot fuming sulfuric acid, hot fuming sulfuric acid, it forms benzene sulfuric, forms benzene, oh sorry, it forms benzene sulfonic acid. In this case, you will have benzene plus concentrated H2SO4. Okay, there will be heat here. This is hot and fuming sulfuric acid. There will be heat here, and we will be forming sulfonic acid. So you will have here SO3H. You will have here SO3H plus H2O. Now, in this, what is the electrophile? So you can write generation of SO3H positive. Okay, so the sulfur is having the positive charge here. Now, how is this generated? We have only one reaction, that is H2SO4. So you can take, you have seen this type of reaction, the H2O, it is It gets dissociated into what? It gets dissociated into, you can write it like this. There is H2O. It gets dissociated into H plus OH negative, right? But this is rather not H plus. What happens is H2O plus H2O. You will get H3O positive plus OH negative plus OH negative. Similarly, what will happen with H2SO4? You just have H2SO4. So 2 H2SO4 plus H2SO4. You are going to get, now one of these will become SO3H. What you are doing here, we are removing one of the hydrogen atoms from one of the hydrogen and one of the oxygen atoms. So you will be getting SO3H positive. So one of this will be acting as a base, the other will be acting as an acid. The other will get HSO4 negative, plus you will be getting water from it, okay? Now this SO3H, it is going to act as the electrophile. HSO4 negative, it is going to act as the proton acceptor. It is going to act as the proton acceptor, okay? You can write this. This is just an example, just an analogy, how things happen. Write this down, let me know if you're done. Yes, done guys? Now, as you can see in all of these reactions, we have substituted one of the hydrogen groups, okay? One of the hydrogen that is attached on benzene. You can write a remark here. In above reactions, only one hydrogen is substituted. Only one hydrogen is substituted or replaced by electrophile. But if excess of electrophilic reagent is taken, then all the hydrogens can be replaced. Okay, can be replaced. For example, if you have benzene ring and you have Cl2 in excess, in the presence of anhydrous AlCl3, all the hydrogens will be replaced by chlorine. Okay, so in this case, you don't need to write the numbers here, okay, because we have hexachlorobenzene. We have hexachlorobenzene. And write this down, let me know if you're done. Are you guys done? Some of you are done. Okay, Parvati is done. Who else? Okay, you guys are done. Now, let us write a next topic, that is the directive influence of substituents and the reactivity. Okay, so right, first of all, effect of substituent, effect of substituents on electrophilic, aromatic substitution. Electrophilic aromatic substitution of benzene and its derivative. So what we will be doing, we will be adding some substituents and we will be looking at what is the effect, of that addition, what is the effect of that addition. Okay. You guys know the mesomeric effect, right? Yes or no? From basic concepts of organic chemistry. Yes, guys, plus M minus M. No, you guys have not heard of plus M minus M.
No, sir.
Okay, mesomeric effect. What about this line? Mesomeric effect? No.
No.
Okay, no problem. So see here. So what we will be doing, we will be adding different type of substituent, and we'll be looking at what is the effect of these additions. What is the effect of these additions? Okay. Now we have many functional groups that can be added. We can add a simple methyl group. We can add OH. We can add carboxylic acid. We can add aldehyde and so on. Okay, we can add many different things. So you all must know resonance, right? Resonance, yes or no? Guys, what happened?
Yes, sir.
Resonance, you all know, na? So I'm just giving you out two resonance. Okay, I'm just giving you out two resonance. So let us say we have CH3, CH2. No, let me not write CH3, CH2. Another CH2 double bond, CH and OH. Okay, so you need to be able to write resonating structures. Now in this case, what is going to happen? You have A double bond B single bond C. Now the resonance will happen something like this, that this lone pair electron will move here and this pi bond will move here. So you will have CH2 negative, single bond CH, double bond OH, and oxygen will get a positive charge. Now a different type of resonance, if you can have CH2 double bond CH, single bond C, which is bonded to a hydrogen, and it is further bonded to a double bond oxygen. It is further bonded to double bond oxygen. Now, in this case, the resonance that will be taking place, it will be something like this, that this oxygen will first of all take the electrons, and it is going to form CH2 double bond CH, single bond CH, single bond O negative, and here C will be getting a positive charge. Now, this bond will move here, and you are going to get CH2 single bond, CH double bond, C single bond O negative, and there will be hydrogen here, and this carbon will get the positive charge. Okay. Now in these two cases, what I want you to see is that there are two types of effect in resonance. There are two types of effect in resonance. I can see that this is our main chain. This is our main chain. This is our organic compound. And OH, okay, in this case, OH is our functional group. OH is our functional group. Similarly, in the second case, I can say that the aldehyde group, that is CHO, it is our functional group. And this is going to be the normal carbon chain. This is going to be the normal carbon chain. Okay. Any problem till here with this classification of functional group and normal carbon chain? I'm not saying it is the main chain, but it is a carbon chain. Yes, in 1 and 2.
Yes.
No problem, right? No problem. Okay, fine. Now we can see that very nicely that in OH, in the OH case, hydroxy group, we are shifting electron. We are shifting electron towards the carbon chain, yes or no? And the carbon, it is getting what? A negative charge. That means OH is donating electron. Yes or no, guys? Through pi bond.
Yes, sir.
Yes. What about others? Huh? Can you guys see this? Yes or no? First of all, tell me that. Yes, Abdul Rahman, Khalil, Mazia, Mehreen, Minashi, Razan, Yusra. Huh, guys?
Yes, sir.
Yes, all of you can see that, right? Yes, okay, fine. Now, if you see the aldehyde group, in this case, we can see that the electrons, these are shifting away from the main chain. It is shifting away from the main chain. And you can see that what is the effect of that? That the main chain, not the main chain, sorry, the carbon chain, it is getting a positive charge here. It is getting a positive charge. That means the CH2 has an effect of withdrawing electron. Through pi bond. Yes or no? Yes, guys, tell me.
Yes, sir.
So if there is a group which is donating electron through pi bond, it is known as the plus M group. That means it is adding electron. And if you have a withdrawing effect, then it is known as the minus M group. So in this case, aldehyde is a minus M group, OH is a plus M group. Fine. Minus M and plus M. Now, first of all, what we need to do is we need to classify all the groups in terms of what is plus M and what is minus M. Okay, what is plus M and what is minus M. You can write this down just so that you know what is the plus M and minus M. Then we can write how to classify a particular group into plus M and minus M. Write this down. Let me know if you're done. Okay. Only Parvati is done. Who else is done? Ms. Abdul Rahman, Khalil, Mazia, Shuaib, Mehreen. Okay, Minashi is done. Okay. Now, in order to classify, we need to, first of all, all of you need to identify something that I call as key atom. Okay, you can write concept of key atom. This is very important. You need to identify the key atom. What is the key atom? In the key atom, what is the key atom? Key atom is in the functional group. The atom in the functional group which is directly attached to carbon chain. The atom in functional group or substituent that is directly attached to carbon chain. Okay, so in this case, we will be just looking at benzene, okay, examples of benzene, because we are learning about benzene. So if you have benzene ring, and then there is a OH group attached, then in this case, oxygen is the key atom here. Oxygen is the key atom. If you have a benzene ring, and you have NH2 group attached here, in this case, what is the key atom, guys? What is the key atom in NH2? Nitrogen, right? Nitrogen is going to be the key atom. If you have COOH, in this case, this carbon of carboxylic acid is the key atom. What if you have CHO? What if you have C double bond O, and then there is some R group here attached? If you have NO2 group, if you have CN group, what else can be there? You have nitrogen, which is attached with C double bond O, CS3. You can also have this is halogen. Yes. So write all of these. Okay, and all of you have to identify whether it is a what is the key atom in these cases. Okay. Yes. Can someone please turn their mic on? Tell me in benzaldehyde, in the fourth one, the key atom is what?
Carbon.
Carbon. Again, if you have some ketonic group, then again carbon. Yes.
Yes.
Yes, sir.
What about this? Nitrobenzene.
Nitrogen.
Nitrogen.
In this, cyanobenzene,
Carbon.
carbon. In this,
Nitrogen.
nitrogen. Here you have carbon, here you have sulfur, and here you have the halogen group. Okay. Done? Yes, guys, done.
Yes, sir.
Okay. Now it's very easy. It is very easy to identify which will be plus M, which will be minus M. Okay, it will be plus M, which will be minus M. So you have the key atom, right? You have the key atom, right? Key atom. Write it in sentence. Okay. Not worry about the flow chart. First of all, you will look like this: key atom attached to more electronegative element, more electronegative element via multiple bond. Then that group is minus M. That means that is electron withdrawing. Group. Now, first of all, you will make sure that it is not minus. Okay, fine. If it is not minus M, then you will move on to if key atom has lone pair. If key atom has lone pair or CS3, I mean not CS3 exactly, but you can write just an or R group, alkyl group. Okay. I am writing alkyl group. We'll write that later. Okay. If it has lone pair, then it is plus M. Then it is plus M. But first of all, you will see that whether it is attached to minus, whether it is attached to electronegative element, more electronegative element via multiple bond. Yes or no? Okay. If that is the case, then it will be minus M. You will not have to look at the lone pair also. So first of all, make sure that it is minus M, yes or no. If it is not, then you move on to the plus M criteria. Then you will move on to the plus M criteria. Let me know if you're done. Done, guys? These two, are you done? Yes,
Yes,
or no? Okay, fine. Now, for the OH case, you tell me, what is the key atom, guys? What is the key atom? Oxygen. Is it attached to any electronegative element? Is the key atom attached to any electronegative element? Okay. Now, tell me.
Yes, sir.
Yeah, which element?
No, electropositive.
It is attached to hydrogen. Okay, so I have to tell what it is attached to. So oxygen is attached to what? Other than benzene. Okay, you don't have to see benzene, please. Okay, oxygen is attached to hydrogen, right?
Yes.
Yes, sir.
Okay, so it is not minus M. We have made it clear it is not minus M. The next question is, does oxygen have lone pair? Yes or no? Does oxygen have
Yes,
lone
sir.
pair? Yes. So that is why this will be plus M. Okay. Same thing. Here we have nitrogen. Nitrogen is attached to which atom? Nitrogen is attached to
Hydrogen.
hydrogen. It is more electronegative than nitrogen, or it is less electronegative than hydrogen?
Less electronegative.
Less electronegative. Okay, fine. So obviously we don't have to check whether it is double bond or triple bond. And nitrogen has lone pair. One lone pair is there. That's why this will be also plus M. Next is carboxylic acid. So carbon is attached to oxygens, obviously. So
More
oxygen is more electronegative. Okay.
Yeah.
So, but is it attached with double bond or multiple bonds? Yes or no?
Yes, sir.
Yes. C double bond O, and then there is a OH. So this will be minus M. Similarly, this also has C double bond O. That is why this will be minus M. Right? This also has C double bond O. That is why this will be minus M. Any doubt till here? Any doubt till here? Tell me. All of you can identify, right? Yes or no? Razan, Minashi, Mehreen, Mazia.
Yes, sir.
Yes, Abdul Rahman. Okay, fine. What about here? NO2. Nitrogen is the key atom. It is attached to oxygen, and it is attached with a multiple bond. Okay, so the structure of NO2 it is something like this. You have nitrogen, the double bond oxygen, and with the native bond oxygen like this. Okay, the native bond oxygen like this. Now you can also write this bond as single bond oxygen. Oxygen will be having a negative charge, nitrogen will have a positive charge. Okay. So this is also minus M because nitrogen it is attached with electronegative element with a double bond. There is also one more case that if the key atom already has a positive charge, then it is going to be, if the key atom has positive charge, it is going to be minus M. Similarly, here carbon and nitrogen, what is the bond? There is triple bond between carbon and nitrogen. Yes, guys, yes or no? You all know this, right?
Yes, sir.
The triple
Yes.
bond. So here key atom is attached to more electronegative element via multiple bond. That's why this will be minus M. Similarly, here also you can see nitrogen, it is attached to carbon, it's attached to oxygen, but this is not having a, this nitrogen, it is attached to carbon, right? It is not attached to more electronegative element. That's why this will be plus M group. This will be plus M group. Okay. Now CS3, you have to remember this. This will be plus M group. If you have alkyl group, this will be plus M. Now, if you look at SO3H, this is going to be minus M. And if I look at halogen, I can see that it is having lone pair. That is why this will be plus M. Okay, so you just write the plus M and minus M in all of these. Let me know if you're done. Mazia is done. What about others? All of you done? Okay. Fine. Now, in terms of the effect of these groups, what I can say that I can divide the effect into two. There will be two effects. There will be, first is the effect on the orientation. Let me write. Effect on electrophilic aromatic substitution, EAS. There will be an effect, there can be an effect on orientation, because once we have a substituent already, right? We have a substituent here, right? There will be some substituent attached, and this will be going to react. This will be going to react with the different electrophilic aromatic substitution that we have seen. So basically, there are only three possibilities, right? Okay, there will be only three possibilities, and there can be an effect on the reactivity. There can be an effect on the reactivity. That means whether if I have this substituted benzene, it is more reactive than benzene, or it is less reactive than benzene. Okay, there can be two cases. There can be two cases: less reactive than benzene or more reactive. More reactive than benzene, or we can have or less reactive than benzene. Okay, less reactive than benzene. Now, in orientation and in reactivity, both of these things, we will for orientation, we are going to look at the plus M or minus M. Okay, whether now this orientation, it is controlled by plus M and minus M. Okay, that means it is controlled by resonance. Basically, we are having resonance here. Okay, where is the electrophile going to attach, whether it is going to attach on ortho or para or meta. This is controlled by resonance. The reactivity, it is controlled by electron donating or withdrawing nature. Okay, electron withdrawing or donating nature. Please remember that when we are talking about plus M and minus M, that is why when you are talking about mesomeric effect, we are just talking about the electron donation or withdrawal with the pi bond. But when we are talking about electron donating in general, we are talking about both of things. That means there can be some shifting of electrons due to pi bond, that is the mesomeric effect, but there can be also some shifting of pi electrons by the sigma electron, that is known as inductive effect. So you guys must have heard about inductive effect, I hope. Yes or no? In term 1, inductive effect.
Yes, sir.
Yeah, inductive effect you have, right? Okay, fine. So when more electronegative element is present in a particular carbon chain, then it is pulling electron, and that is why we have the inductive effect. Okay, that is, so we have to look at the net effect of electron or withdrawing nature. That will be controlled. That will be controlling the reactivity. For orientation, we have only two things, that it will be either +1, +m, or -m. It will be +m or -m. So now let us, what we can do is we can write the orientation. We can write for the orientation. So for orientation, there can be two things. Orientation, you will have +m or -m. So if you have +m group, then electrophile will attach. Attacks on ortho and para position. If there is a meta group, sorry, if you have -m group, yes, Mehreen, just wait a second, let me write this down. Then electrophile attacks on meta position. Yes, Mehreen, you can write this down. Let me know if you're done. Yes, yes.
Done, sir. Thank you.
Okay. Done, guys, with the orientation. Yes, are you done?
Yes.
Yes, sir.
Okay. Yes. So for +m and -m, you can see some reactions. So you can write some examples here. So if I will have a OH group, and let us say we are doing here nitration. I'll just write it like this. We're doing nitration. So you will be getting two products. OH, there will be ortho product NO2, plus there will be a meta product. But because it's a +m group, right? This is a +m group, that is why ortho and para, sorry, ortho and para position. You can write this is O nitrophenol. This is P nitro phenol. But let us say if you have some groups such as CN, if I am doing nitration, then I will be getting only one product, that is the meta product. That is the meta product. Here there will be NO2. right? Write this down. Let me know if you're done. Now we will look at the reason why do we get uh, ortho and para product if you have a plus M group. This was the example of plus M group. And why do we get a meta product if we have a minus M group? Write this down. Let me know if you're done. Done? Is there anyone who is still writing? No? Can I move on then? Okay. Now let us look at the plus M. Plus M group. So we are taking the example of OH. Okay, but you can elaborate to any of the plus M group. You have OH here, which has lone pair. There will be a resonance like this. We'll be making a double bond here. This electron will go here. Have OH. This will be positive. These bonds will be as it is. And this carbon will get a negative charge. Now you can see this can move this side. This bond will move on this carbon. Now again, what will happen? The same double bond O will be there and H will be there. This is completely intact. Nothing is happening to here. But this bond is also completely intact. Nothing is happening here. Here we have formed a bond and this bond has been broken and this carbon is getting a negative charge. Similarly, you can see in the next thing what will happen. This will move here. This bond will move on this carbon atom. So you have OH, again a positive charge. This complete bond is intact. Then we have new bond which is formed here and a negative charge in this carbon atom. Then this will negative charge will go here. This will go to the oxygen and it will be lone pair. So we have shown the complete delocalization of the pi electrons. We have shown the complete delocalization of the pi electrons. We have OH and here we have double bond. Here we have double bond and here we have double bond. Now, in this case, you can write the resonating structure something like this. It will be the sum of resonance hybrid structure. Sum of all these resonating structures. Now I can say that all of these bonds are partially, these are all partial double bonds. This bond is also partial double bond. This OH. Now oxygen in all of these structure, in the 3 of structure, it is having a delta, it is having a positive charge. So I can write that this oxygen will be having some positive charge. And I can also show that this position is having some negative charge. This position is sometimes getting negative charge and this position is sometimes getting negative charge. Now you can clearly see that this position is the ortho position and this position is the para position. So since there is an increase in the electron density at ortho and para position, that is why plus M groups are ortho para directing. Since there is an increase in the electron density at O and P when plus M group is attached, Hence, they are ortho and para directing for electrophilic aromatic substitution. Electrophilic aromatic substitution. You all guys got this right? Yes or no? Why the plus M groups? These are orthopara directing because we are attacking an electrophile. When an electrophile is there, it needs electron, so it will be attacking. It will be attacking on those sites which have more electron density. And if we have a plus M group, then ortho and para positions are those positions which have more electron density than the meta one. That is why preferentially we will get ortho and para products. Ortho and para products. Write this down, then we will look at the minus M group. Okay, write this down, then we will look at the minus M group and why. Now, obviously, you can understand that in minus M group there will be something happening in the something, or rather we can say that relatively the meta group will be having higher electron density. Yeah, let me know if you're done, guys. Yes, is everyone done? No. Okay, Minashi is done. Okay, all of you guys are done. So let me just scroll down. And let us look at minus M. What? Did someone say something? Hello? No? अरे भाई कौन है ये इतना धीरे कौन बोल रहा है? Who is this? Khalil is Abdul Rahman. Okay, fine, but speak loudly a bit. Please. Write this down. Let me know if you're done. Okay. So minus M group. So let us take NO2, which is the highest minus M group, most minus M group. So what is going to happen in this case is that you will get, so oxygen will first of all take the electrons, and then on the nitrogen atom you are going to get a positive charge. Okay, then this electron is going to form a double bond. There will be a shift of electron due to resonance. Here you will be having a double bond nitrogen, oxygen and oxygen, right? There's a dative bond here, and here it will be having a negative charge. Okay, now in this case this bond is intact, this bond is intact, but this carbon atom, it will be getting a positive charge here. Now after that we can see that there is a resonance that can happen. This bond will shift here, electron source to electron sink. That means more electron rich to electron poor. This will be intact like this. Here will be having negative, here will be having okay. Now this bond will be formed. This bond will be there. This carbon will get a positive charge. Again, you will have N oxygen, oxygen double bond. This bond will shift here. This carbon is going to get a positive charge, and you'll have bonds like this. Okay. Next, what is going to happen? You will have negative charge here. This bond is going to shift this sign. This bond is going to shift this sign, and you will be back to the nitro. So you have a bond here, you have a bond here, you have a bond here, and then you will be having nitrogen, double bond oxygen, single bond oxygen with a dative bond here, with a dative bond here. Okay. Now for this, if I want to make the resonance hybrid structure, then I have to make something like, so there will be nitrogen, and let me just write O2. I don't want to worry about the bonds in nitrogen and oxygen. I just want to worry about the electron densities in the benzene. So obviously speaking, this all will be partially double bond, because all of the bonds are sometimes double, sometimes single. That is why partially double bond. But what I can say is that it will be delta positive here, because it is having positive charge sometimes here. It is having sometimes positive charge in the para position and also in the both the ortho positions. This is also kind of double bond here. Okay. Now for this, I can say that in minus M, rather if minus M group is attached, then it decreases the electron density at ortho and para position. Hence, the meta position, has relatively higher electron density than O and P. This is why minus M is meta directing for electrophilic aromatic substitution. Write this down, let me know if you're done. Yes, done all of you?
Yes, sir.
So we have not